So we're back to talk more about trig functions and complex numbers, primarily in this lecture only trig functions. We're going to skip through these previous slides that we talked about and land here on the unit circle. So recall this is the unit circle. It is a way to define sine and cosine based on a circle with a radius of 1 and an angle defined as a counterclockwise angle for the x-axis. What the unit circle does is it allows us to define sine and cosine throughout a full revolution around the unit circle, which goes from 0 to 360 degrees or 0 to 2 pi. So we don't have to have a triangle. We basically can have a point location on a defined xy coordinate, and we can find the sine and cosine and tangent and other trig functions of the angle that is subtended between the x-axis in a counterclockwise direction to the line from the origin to the point. So given this, the vertical distance from the x-axis defines the sine, since the hypotenuse is 1. The horizontal distance from the y-axis defines the cosine. So that's the usefulness of the unit circle. There are some significant triangles that if you took a high school trig class, you should have covered. I don't know how much high school trig classes or even college trig classes work on this anymore, but I know that throughout your engineering classes, people will just expect you to know the sine and cosine of the 30-60-90 triangle and the 45-45-90 triangle. And so conveniently here on the unit circle, the cosine and sine in that order are given for points at various angles in various quadrants. I want to draw your note to the fact that the tangent of 90 degrees does indeed go to infinity. The tangent of 0 degrees is 0. And then there are a couple of the transcendental functions, cotangent and cosecant, which we don't use a whole lot, that also go to infinity at various angles. So if you're doing some calculations and you're trying to find the arctangent, which is the angle whose tangent is, and you come up with infinity, don't panic or freak out, because the tangent actually does have an angle that results in a value of infinity for the tangent. So if you would like to make a copy of this, I do not expect you to have these memorized for your next quiz or exam. It's just a useful thing to have for your future. All right, this does bring into play. Let's go back. Note up here we have both radians and degrees listed. In general, if you want to convert from radians to degrees, if you're given degrees, you multiply by pi, divide by 180, and that'll give you radians. If you're given radians, multiply by 180, divide by pi, and that'll give you degrees. We tend to see degrees used a lot in construction, surveying, etc. We tend to see radians used in engineering and physics. However, in electrical engineering, you'll sometimes see these units mixed. So, for example, you may have within a single cosine function one angle in radians and one in degrees. And so obviously to add those, you'll have to do a units conversion, and we'll show an example later. All right, here's a plot of the cosine of x, and there's a little error in the PowerPoint slide. It's actually plotted from 0 to 30, which should be obvious to you looking at the graph. I plotted this on MATLAB, starting at 0, ending at 30, going in steps of 0.01. Defined that to be my x array, then found my f, which is the cosine of x, and then asked it to plot. I didn't do anything fancy with any labels because I knew I'd be making the video, but obviously you could give this a label and you could play with your fonts and your line thicknesses, as we discussed in a previous video on plotting. So notice here the cosine function just has an amplitude of 1, and so you see on this plot that the value runs from 1 to -1, which you already knew. We refer to the max and min to the maximum value or to the absolute value of the minimum value as the amplitude or magnitude of the cosine function. So if this had a multiplier of 10, it would have a magnitude of 10. You can either read that directly from the cosine function, or you can sometimes see it in a graph. Also note that the function repeats itself. So in other words, if you start at any one point and you go to the value of 2 pi, which is a full revolution, you'll have a full repetition of the cosine function. And that's the case anywhere you start or stop, you'll end up after 2 pi radians at exactly the same spot. Now, MATLAB generally defaults to radians. So when I entered this, I did not specify that this was radians or degrees. Note it defaulted to radians. The cosine function is equal to 1 at integer multiples of 2 pi. So 0 for 2 pi, 4 pi, and so on. Now this is once again just a table for your reference. I realize a lot of you have not had calculus, or you're in calculus now and maybe you never had it in high school. If that's the case, don't worry about that. This is just, once again, one of those tables that might be useful to you if you have had calculus. I know that I constantly have to think about, I have to literally visualize the slope of the function to remember whether the derivative is positive or negative. So that is not an automatically memorized thing to me. So if it's not to you, this might be a useful table also to print out that has all of the derivatives and integrals for the 6 major trigonometric functions. All right, I want to, at this point, stop the video and we will come back and pick up with sinusoidal functions and waves.